Hey guys, welcome. Yeah, so in this video, we're going to define what we mean by rings in mathematics, and we're also going to see 3 examples of rings. And rings are something you first encounter typically in abstract algebra after you study groups. In fact, it's very important that you first learn about groups before you study rings, because as you'll see shortly, rings are first and foremost abelian groups under addition. So in math, a ring is a set together with 2 binary operations, plus and star, where plus is usually addition and star is usually multiplication. Now, one important distinction then between groups and rings is that groups come with 1 binary operation, whereas rings come with 2 binary operations, yeah? And as I said, rings must be abelian groups under plus, under addition. And I also already said this footnote, but yeah, so because rings have to be abelian groups under addition, they must fulfill all the requirements of abelian groups. That is these guys, right? Now, notice that I say star must also be closed, right? And so that's the requirement for a ring because, well, a ring comes with 2 binary operations, and therefore we require that both be closed. Whereas, for a group, it only comes with 1 binary operation, and we require that that binary operation be closed, right? Okay, cool. So, closure of plus and associativity of plus and commutativity of plus is actually what makes it an abelian group under addition, right? But yeah, closure, associativity, and additive identity and additive inverse, those make it a group. And then the plus being commutative makes it an abelian group. And yeah, but for a ring, we don't just require that it be an abelian group under plus. We also additionally require these 2 things. One is right and left distributive properties of star over addition. So left and right distributive properties. And so we'll see examples. So we'll see exactly what we mean by left and right distributive property. And the distributive property will be for star over plus, yeah? And the majority of authors, and therefore the majority of books, will also require that star be associative. So I am saying that there are rings where star is not associative. In fact, our first example will be such a ring, yeah? Okay, cool. So in summary, a ring is an abelian group with the distributive property of star over plus, and star is associative. So these additional 2 requirements plus abelian group under addition, right? And when I say abelian group here, I mean under addition, but I've already spelled that out here, right? Okay. So yeah. All right. So let's get on with the examples. Examples of rings. So the first example, as I said, will be one where star is not associative. And for that, let's take vectors in R3, where plus is usual vector addition, and star is the vector cross product. Okay. Yeah, then we know that vectors in R3 with respect to addition form an abelian group. You can, check that more carefully if you want, but it goes without saying. So all we have to do to see that these guys make a ring is check the additional 2 requirements. Well, actually, one of the 2 additional requirements, the distributive property of cross over plus, because as we said, not all rings have to have star be associative, and therefore here, cross product does not have to be associative, and that's why we picked this example in the first place. But yeah, what I've demonstrated here is the right distributive property of cross over plus, right? This is what we call the right distributive property. And this is true. We know that if we take 3 vectors a, b, and c, and we do a plus b cross c, it's equal to a cross c plus b cross c, right? Okay, and this is the right distributive, but we also need left distributive, so we need this, and this is also true. But as I said, we know that the cross product is not associative. It's not necessarily true that a cross b and then cross c would be equal to a cross b cross c. So because of that, this serves its purpose. So for our second example, let's take 2 by 2 matrices where plus. So for our second example, let's take 2 by 2 matrices where So for our second example, let's take 2 by 2 matrices with real entries. So for our second example, let's take 2 by 2 matrices with real entries where plus is typical 2 by 2 matrix addition and star is matrix multiplication. Then we will have a ring, and this is so because we know that 2 by 2 matrices under matrix addition form an abelian group. It's easy enough to check, so I could leave it up to you, but let me do a little bit of hand holding. If we take an arbitrary 2 by 2 matrix called capital A here with real entries A, B, C, D, and then we take the 0 matrix to be the additive identity, and then we take the additive inverse to be this matrix, then we have the existence of an additive identity, the existence of an additive inverse, and clearly 2 by 2 matrices are closed under addition. So we have that, right? And we know that matrix addition is associative and commutative. Matrix multiplication is not commutative, but matrix addition is commutative and it is associative. And so we see that we have 2 by 2 matrices under matrix addition form an abelian group. And as I said, it's easy enough, or as I may not have said, it's easy enough to check that 2 by 2 matrix addition is commutative and associative. You could just take 3 generic 2 by 2 matrices with random entries, well, where the first one is A, B, C, D here, where the entries again are real, and the second one could be like with entries S, T, U, V, and whatever, and you can check that, with easy enough algebra that addition of 2 by 2 matrices is both commutative and associative. Yeah? And of course, for a ring, we also need to additionally check these, right? Which is the fact that the sum of 2 matrices when it is multiplied on the left by a matrix A will be the same as having the matrix A multiply one of the 2 matrices and then adding that to the matrix A multiplying the other matrix. So this is the left distributive property of star over plus, right? And we also need the right distributive property to be fulfilled, right? And the luxury additional requirement for a ring is to check that star, in this case 2 by 2 matrix multiplication, is associative, and it in fact is. 2 by 2 matrix multiplication is not commutative, as matrix multiplication is not typically commutative, but it is associative. Yeah? Okay, cool. And on to our final example. And I don't do much or say much here in this last example, but this last example is the ring of numbers of the form a plus b root 2, where a and b are in the integers. And you could do a little bit of algebra to see that we have a ring here. If we take plus to be the usual addition and star to be the usual multiplication. Yeah? Okay, multiplication and addition of real numbers. Okay, so that's it for this video, and I hope you enjoyed it, and I hope you learned a lot. Keep watching. Take care.